Accelerating Java Microservice Deployment with AI-Driven Dockerization. Welcome, fellow developers and IT enthusiasts. Have you ever felt the relentless grind of deploying a Java microservice? That familiar cycle of meticulously crafting Docker files, endlessly tweaking configurations, and then constantly second-guessing if your resulting image is truly optimized for production. It's a pervasive bottleneck in modern development workflows, isn't it? We pour countless hours into perfecting our Java code, only to find ourselves navigating a maze when it comes to packaging and deploying it efficiently. Manual Docker file creation, while a fundamental skill, can often lead to suboptimal choices, think bloated images, agonizingly slow build times, and even subtle security vulnerabilities. But imagine a different reality. What if there was a smarter, more intelligent approach? A way to automatically generate highly optimized, secure Docker files, precisely tailored for your unique Java applications, without the guesswork. Today, we embark on an exciting journey into the world of AI-driven Dockerization. This revolutionary approach promises to significantly accelerate your Java microservice deployment pipeline by harnessing the transformative power of generative AI. Prepare to reshape your DevSecOps practices. The challenge isn't just about writing a Docker file, it's about writing an optimal one. When developers manually create Docker files for Java applications, they often face a dilemma. Should they use a full JDK image, making the final image unnecessarily large? Or struggle with a minimal JRE, potentially missing crucial dependencies? How do they ensure proper layer caching to speed up rebuilds? What about running the application as a non-root user for enhanced security, a best practice often overlooked? And the complex world of JVM tuning within containers, memory limits, garbage collection, and container-aware JVMs, these are intricate details that demand deep expertise. Without precise optimization, you end up with heavyweight images that consume more resources, take longer to deploy, and introduce unnecessary attack surfaces. It's a constant battle where manual efforts often fall short. This is precisely where generative AI steps in as a powerful ally. Imagine an intelligent system, trained on colossal datasets of optimized Docker files, best practices, security configurations, and application frameworks like Spring Boot. This AI isn't just a pattern matcher, it's a deep learning entity capable of understanding the context of your Java project. When you feed it your project's metadata, perhaps its pom.xml dependencies, the Java version, or even runtime characteristics, the AI can analyze these inputs. It then intelligently synthesizes and recommends an optimized Docker file. This paradigm shift means less manual trial and error for developers. The AI can identify opportunities for multi-stage builds, recommend the leanest possible base images, suggest appropriate non-root user configurations, and even provide tailored JVM arguments. It transforms a complex, knowledge-intensive task into an automated, AI-driven process, ensuring consistency and adherence to best practices across your microservice ecosystem. To illustrate this cutting-edge approach, we've prepared a simple yet highly representative Java microservice for our demonstration. We've named it AI-OptiDoc-Java. This is a classic Spring Boot application, designed as a minimal Hello World REST API. You'll find its core logic within AI-OptiDoc-Java application.java, exposing a straightforward /API/hello endpoint that simply returns a greeting message. The project uses Maven for dependency management, as defined in its pom.xml file, which includes standard Spring Boot web starters. This setup is deliberately uncomplicated to keep our focus squarely on the Dockerization process rather than complex business logic. However, despite its simplicity, it perfectly encapsulates the common challenges and optimization opportunities inherent in containerizing any Java application. It's the perfect canvas to showcase how AI can analyze, understand, and then generate a truly optimized Docker file for a real-world Java project. Now, let's peel back the layers and examine the brilliance of an AI-recommended Docker file. The first and arguably most impactful optimization is the implementation of a multi-stage build. Instead of one monolithic Docker file, the AI splits it into two distinct stages, a build stage and a final stage. The build stage leverages a robust Java Development Kit (JDK) base image, providing all the necessary tools for compiling our Java application with Maven. Crucially, the AI ensures layer caching is optimized. It instructs Docker to copy pom.xml first, before copying the entire source code. Why? Because pom.xml changes far less frequently than source code. By copying it early, Docker can cache the MVN dependency, go offline step, dramatically speeding up subsequent builds. After compilation, only the lean, executable JR from the build stage is copied into the final image, which uses a much smaller Java runtime environment, JRE, base image. This strategic separation ensures your production image is remarkably compact, discarding all heavy build time dependencies. Beyond multi-stage builds, the AI-recommended Docker file introduces critical security and performance enhancements. A prime example is the shift to running the application as a non-root user. Our AI-generated Docker file includes commands to group add and user add a dedicated user, typically named Spring, and then explicitly switches the user directive to this non-privileged account. This is a fundamental security best practice, significantly mitigating potential privilege escalation attacks if a vulnerability were to be exploited within the container. Furthermore, the AI intelligently recommends JVM tuning parameters tailored for containerized environments. By setting Java_OPTS environment variables like XMS256M, XMX512M for initial and maximum heap sizes, and crucially, XX, plus use container support, the JVM becomes aware of its container's resource limits. This prevents Java from attempting to consume more memory than allocated, leading to more stable and predictable performance, and gracefully handling resource constraints. To bridge the gap between concept and practical demonstration, we've created a Python script called recommend_dockerfile.py. In a live, enterprise-grade scenario, this script would act as an orchestrator, dynamically interacting with a sophisticated generative AI service, like a powerful LLM. This interaction would involve feeding the AI detailed project metadata, think language versions, framework specifics, and detected dependencies. The AI service would then process this information and synthesize a unique, highly optimized Docker file tailored precisely for that project. However, for the purpose of this demonstration, our recommend_dockerfile.py script cleverly simulates this AI behavior. It contains the predefined, carefully crafted content of an optimized Docker file, representing the output a real Gen AI tool would produce. When executed, it simply writes this optimized content to a file named dockerfile.recommended. This allows us to vividly showcase the AI's impact without requiring a live, complex AI inference engine. Let's bring this to life with a quick, local demonstration of our AI-driven deployment workflow. The process is remarkably straightforward. First, as developers, we start by building our Java microservice. We simply navigate to our project directory and execute the familiar Maven command, mvn clean package, skip tests. This compiles our Java code and packages it into an executable JR file, ready for containerization. Once our application JR is successfully built, the magic begins. We then invoke our simulated AI recommendation script, Python 3 recommend_dockerfile.py. In mere moments, this script